So we've been talking about linear growth and exponential growth. And so what we want to do in this last activity is look at some different scenarios and determine whether it represents linear growth, linear decay, exponential growth, exponential decay, or neither. So let's remind ourselves, linear growth is going to be characterized by a constant rate of change, and that rate is positive. Linear decay is going to be represented by a constant rate of change where that number is negative. Exponential growth is going to be characterized by a percentage increase, a fixed percent increase. Exponential decay by a fixed percent decrease. If it's none of those four, then it would be neither. So I would like you to pause the video and look at these 5 scenarios and decide if it's any of these 5 options here. Now, this is not a one-to-one thing. Like, you could use linear growth multiple times if you wanted to, or linear decay. All right, give it a shot. Pause the video and restart it when you're ready to go. All right, let's take a look at A. The current world population is about 7.7 billion, and it grows by 1.1% each year. So we certainly see here a fixed percent increase. We have a fixed percent increase. So that is going to be exponential growth. I'm just going to put 3 here for exponential growth. Looks like candles. B, Heather owns a lawn business and earns $20 an hour. $20 an hour. So that is a fixed amount of a rate of change. The amount of money she makes is going to increase at a constant $20 per hour. So that is linear growth. So we have a positive constant rate of change. I can't fit that here. I'm going to write rate of change. Okay, so that is option 1. C, John has $40 on his bus pass and $2.50 is subtracted from his balance every time he rides the bus. $2.50 is subtracted from his balance. So he is losing $2.50 worth of value for every ride, per ride. So there we see a negative constant rate of change. Rate of change. So that is going to be option 2, linear decay. It'd be kind of good if you could think about writing an equation for these. Maybe we'll go back and think about that. Okay, D. A ball is thrown straight up in the air. Some data on the ball's height above the ground is given in the table. So let's take a look. Let's first check for linear. So to check for linear, we would want to see if this is increasing or decreasing. It looks like it's increasing. So 6 feet to 54 feet, that's an increase of, what, 48 feet? And this is an increase of 16 feet. So that's not constant. That's not a constant increase. So it's not linear. It's not linear. It's not linear decay because it's not getting smaller. The height is going up. So the only option there was maybe linear growth. All right, let's try exponential. Is it exponential? So in this way, we have to think about if we could multiply by a certain percent. It's definitely increasing, so could it be exponential growth? It's not exponential decay because the heights are getting greater. So we have to ask ourselves, is there something, if I multiplied 6 by something to get 54, would I multiply by 54 by that same number to get 70? Doesn't look like it, does it? Let's see, I think actually 6 times 9 is 54, right? Well, if I take 54 times 9, it's not going to be 70. So it is not. That guy's eye looks like he got punched in the eye. There we go. That's why he's sad. So it's definitely not exponential growth. Well, I guess that means it's neither. So that was option, what was that, 5? Option 5, neither. Okay, option 5. Why do I keep wanting to do parentheses? I don't know. Option 5. Last one, E. The value of a 1989 LeBaron convertible decreases over time. Some data on its value is shown in the table. So we got this keyword of decrease, so we really need to look for if it's linear decrease, linear decay, or maybe exponential decay. Okay, so let's check for linear first. That's easiest. We just have to subtract these numbers and see if it's a constant. So I'm going to take 17,196 minus 8,598. So that went down by 8,598 decrease. Okay, let's subtract the next two. 8,598 minus 4,229. That's going down by 8,169. So that's not constant. 8,000. That's not 8,000. That's, see, this is good. You have to look at the answer and say, does that make sense? It's going from 8,000 to 4,000. I mean, it can't be 8,000. It's got to be some. So I actually didn't punch in one of the 2's. Always check your answer for reasonableness. How about 4,300? That seems better. And 69. Okay, so that's not a constant decrease, so it's not linear decay. I'm not even going to check the next one. Now, for exponential, we have to think about, is there something I could multiply 17,196? Is there something I could multiply that by to get 8,598? Well, there is something I could multiply it by, but I have to figure out what it is. This is a little bit tricky. We haven't really covered solving equations like this, but the way that you're going to figure it out is you're going to divide. All right, so to figure out what this number is, and some of you that have had a little bit of algebra experience this may start to ring some bells, but you're going to take 8,598 and divide it by 17,196. So let's do that. 8,598 divided by 17,196 is 0.5. Wow, I didn't really recognize that as half. That means that 8,598 is exactly half of 17,196. If the numbers were a little nicer, I probably would have noticed that, but I did not. So that means that this is a 50%. So it's a 50% decrease. We're multiplying by 50%. This is the one case where the decrease is equal to the multiplier, right? If you decrease by 50%, you're retaining 50%, so your multiplier is 0.5. All right, well, let's take 8,598 and times it by 0.5, 50%, and see if we get 4,229 times 0.5. How about that? We did. Huh. All right, so let's take 4,229 and times that by 0.5. I got $2,149.50. So that was kind of tough to see, but this actually is exponential decay. This actually is exponential decay. All right, so just for kicks, let's go back and see if we can write some equations. Let's do this equation right here. This is good practice because students kind of struggle with equations sometimes. So let's call this value V, and let's call this T years. So to write my formula for exponential decay, I'm going to say my value started at $17,196, and then what did I multiply by? 0.5. And how many times would I multiply by 0.5, say, to get down here to 3 or to 15 years? Right, however many years there are. So that's going to be to the t power. exponential decay is always going to have the variable in the exponent. That's a good little way to remember that. Okay, we're not going to do D because that was neither. Let's do C. So remember, this one was linear. So let's say that B is the balance that he has on his bus pass, and R is the number of rides. Okay, so let's write an equation. What would his balance be? Well, where did it start? What was his starting balance? It was $40, and then what happened? We subtracted $2.50 for each ride, so we would multiply that by the number of rides. If he did 4 rides, we would take $4 times $2.50, that'd be $10, and we would subtract that off the $40 to find his balance. Make sense? If he rode the bus 6 times, you'd have to see how much money did he spend. So you would take 6 bus rides times $2.50. Whatever that is, you would subtract it off the original balance of $40. All right, how about Heather and her lawn business? Let's say M is the total money made. Total money made. And H is the number of hours worked. Can you write the equation for this one? Give it a try. How would you find the total amount of money made? I think you got it. I'm confident in you. $20 for every hour, right? However many hours she works, you would multiply that by $20. And that would give you the amount of money she's made. If you want to think of the starting, I kind of like thinking about what am I starting with, like we did with this bus balance down here. I started with $40 and then I spent $2.50 per ride. Well, if you think of Heather's business, she started with nothing and then she's adding $20 for every hour she works. All right, so that gives you that same thing there. All right, how about this population one? Let's say P is the population, and T is the number of years. Well, we'd have to have a starting date. The current world population, number of years since 2021. So let's say the current world population is in 2021. I don't know if that's the accurate number, but okay, so what would the population be T years from now? Can you write that equation? Give it a try. All right, what's the population starting at? Starting at 7.7 billion. So let's say this is the population in billions. Then we don't have to write out all those zeros. Since it's a percent increase, we're going to multiply by the multiplier. What would the multiplier be for a 1.1% increase? Be 100% plus 1.1%, which is 101.1%. So your multiplier, you'd move the decimal 2 places over here to get your multiplier, which would be 1.011. And we would multiply by that multiplier for every year after 2021. So this is exponential. We would multiply by that however many times we needed to get the population in some subsequent year. So if we wanted the population, say, for 2030, well, that's 9 years from now, right? So the population, we would take the 7.7 billion we have, and we would multiply that by 1.011, which is 101.1% of the 7.7 billion. And we would do that 9 times because there's 9 years between 2021 and 2030. All right, so these ideas of exponential growth and decay and linear growth and decay are some of the most important ideas that we have in this course. So spend the time thinking about them, going back over these examples, and reaching out with any questions that you have.